Hi everyone. Today I'm talking about how the future is native and ways in which Java is learning to interoperate better with native data. It's a lot of fun to be back here at JVMLS. I missed last year, so it's good to see lots of familiar faces and new faces as well. So my slides, of course, have to start with our safe harbor claims of everything I say is a lie, don't trust anything, don't make any decisions based on what I'm saying. We'll all be sick of these slides by the end of the talk, or by the end of the conference. So who am I? For those who don't know me, I'm the interpreter team lead on J9. J9 is IBM's independent implementation of the JVM. I've spoken here in the past related to 292, Invoke Dynamic, and 335 for Lambdas. I'm also the guy who's responsible for IBM's implementation of those. So if you want to talk about those as well, come find me later. And I've previously done a lot of work with the verifier. So what am I talking about today? The purpose of this talk is to tell everybody here that if you care about native data, you need to get involved. You need to make your use cases known. If you're doing native data, if you're writing a lot of JNI code, if you're using unsafe, direct byte buffer, whatever it may be that you're doing, you need to surface those use cases. We want to know what they are. We want to be able to use those to help drive the direction of native data interop. We have ideas, we have experience with a number of different things that we've done with prototypes, but we want to know what you're doing and how these directions fit with solving your problems. So, I will repeat this again at the end with some more details on how to get involved, but really this is about asking you to share your experience. So, here's what I'm going to talk about. I'm going to start by taking a look at packed objects. Packed objects was an experimental feature that we added in Java 7, and we addressed a bunch of interesting problems with data locality and dealing with off-heap. So, we'll take a look at that. We'll take a look at how we've used that experience to help drive our contributions to Panama and Valhalla, and then we'll look at layouts, which is coming out of Panama, and some of the open issues. So what is packed objects? Back in Java, after we released Java 7, we'd done a bunch of work. We wanted to get that out there. Wasn't quite time to release Java 8 yet, so we put out a technology refresh we called Java 7.1. And in that, we had a packed objects as an experimental feature that you could try. Why did we put this out there? We wanted people to have an option to improve the serialization and I/O of Java objects. We wanted to be able to make it easier to work with native data, and we wanted to remove a lot of the overhead of dealing with small data and improve data locality. And we wanted something that you could write easy Java code with. So if we take a look at a simple layout in Java, this shows a hash table. Some of you may have seen slides like these before. I may go fairly quickly through parts of this. This is mostly about what we've done and an experience report on packed and some of the open design issues and design challenges we have. So here we've got some Java code. You've got a hash table. It points to an array. Each of the entries in there is an object, right? But we've got some overhead. We've got a header on each of these things. And to reference anything in here, we do a lot of pointer chasing. So we've got to walk our way through to actually do any lookup. These may be spread all over the heap. So we've got cache misses and other kinds of problems. And locality, right? There's no claim that any of the fields that you want to touch are actually nicely together. They may be spread out. You're looking at this and thinking this is a simple example. Yes, but we've seen, it's not uncommon to see customer code that has hundreds of fields. And there's no reason that these fields are going to be connected nicely together. So what are we trying to solve? Well, locality problems come in other flavors as well. If you had a class and it had a bunch of fields and you wanted to say that these two fields get used together, so I'll declare them together in the source, that doesn't actually help you. The JVM's free to reorganize your fields, and it does. We want to put longs and doubles together so that we don't waste space. They need to be aligned on 64-bit boundaries. We want to put objects together. It helps the GC. And then, we may even have cases where a superclass had some padding in it, and a subclass can stick a field in there and make use of that padding, right? So we've got no guarantees from the JVM on how your object's laid out. So that's on heap layouts, and then we've got native code here, and maybe I've got a native array events, and I really want to be able to access that array, and I really want to be able to access it as though it was a Java int array. I want an easy solution, right? I don't want to have to write JNI code. I don't want to have to get into unsafe or DBBs. I don't want to have to marshal this data. Okay, so we've got the idea of how do I do away with headers? How do I bring these objects together? How do I flatten this data? And how do I allow better native interop? If I take a look at this structure here, I've got two structs. I've got an address. It's got a char array to give me the address. It's got a short for a port, and I've got some struct called a header, which has two of these things. So I've got them, nicely sitting together. This was where we started when we started looking at packed objects. How do I get a layout that looks like this in Java? And this is why we developed packed. This was our prototype to address some of these things. So if we want to start looking at packed objects under the cover, what we're going to do is we're going to show some examples of very simple Java code, and then we're going to show the packed equivalents. This is not because I'm trying to say, oh, go use packed. It's because I want to show you how we developed our solution for this, and then get into some of the open issues there. So I've got a point here. It's got an x and a y. And if I want to make the packed equivalent, here's what it looks like. Wait a minute, though. It's bigger than the normal point, which kind of goes against the goals that we set out in the beginning. We wanted to make things smaller and pack things together, and here I've gone and added two fields. So what are these fields for? The target is always going to point to the object that owns the data, and the offset is going to be relative to that, to the target, and going to tell you where the data starts. This is the standard unsafe addressing mode. If you've played with unsafe, you've seen these same kind of address modes. Right, here's just the picture with the points or the lines showing where they point to. So if we actually want to read this data, we go target plus offset, and there's my data. All right, so now I've got a line. It's got 2 points in it, right? In standard Java, it looks like this. In packed, it looks like this, right? We've got the data directly in line in the packed line. So here's where, depending on the size of my headers, I'm starting to win footprint-wise. I've improved the locality of this because now it's right there in one thing. And we see the target points to itself, the offset points to the start of the data. Great. And I still have those 2 points. They're each directly in line here. And the code looks pretty reasonable for Java code, right? It seems to be the code you would want to write. Though it does have a couple of at packed annotations. All right, so going back to just this, if I want to then access one of my points in here, how do I do that? How does the model work? So I write the code that says a packed line.e, and I want that to be that second point. First, the source for this looks like normal Java code, which is both good and bad. It means it's very easy to write the code, but it also means that it doesn't do exactly what you thought it did. So when we write this, we actually have to poof up an object header. So your access to this is through this extra object header that we grew, and as we note, the target points to the packed line, the offset points to the data that I want to talk about here for my particular line, so it's easy to access. You may be thinking, wow, a lot of operations, this is going to be a lot of GC pressure, but in hot code, a lot of this can be optimized away. The JIT doesn't have to create these extra headers. And there's still, we're still GC safe. There's no real internal pointers here, at least not without the direct pointer to the packed line. Okay, so if we want to take this and we want to extend it to native access. We have some data in a struct that looks just like our point. It's in native memory. What does the Java code for this look like? Well, looks like exactly what you want it to look like. So how do we tie these two pieces together, right? Again, it's the unsafe addressing mode. except this time our target is null and our offset is an absolute address. So if we wanted to build something in C, going back to my address and header example, we'd expect something that looks kind of like this. It's got a number of good things going on here. It's got the nested substructures, it's compact, there's no headers, and it's got good alignment for getting access to the data. So if I wanted to build this same thing in Java, right, we're back to Java is all about memory. I've now got headers again. I've now chasing pointers. I've got no locality. I've got no guarantees that these things are close together. Something has to give here if we want to be able to get back to that nice native structure. So if we did this in packed objects, you end up declaring very similar Java code to what you want this to look like, and we've got this structure crammed nicely underneath. Right, we're still on heap though. But we've definitely increased the locality of this. So if I wanted to do this with Java and I wanted to access something that's off heap, how would we do this, right? I've got my native structure still, it looks the same, how do I talk to it? The first tool most people reach for is JNI. You play the usual, I want to stash a pointer in a long trick, and there's a lot of overhead here. JNI, one, isn't fun to write, nobody enjoys it. People frequently get it wrong. Most VMs have a check mode to make sure that your JNI code is correct because it's very easy to accidentally stash a local ref somewhere where it shouldn't be stashed, use it from the wrong thread, or use it after you've returned. JNI is slow. You have to process things so that the GC is able to run. You have to build the right stack frames. You need to pass out indirect references for things. There's a high cost to do JNI, especially if all you want to do is a field read. So people often either cache those things, you look it up once and you cache it internally, or you do some other kind of game where you copy the whole data in. Or you move to a direct byte buffer. Right? You don't have to write JNI, which is good, easier to get right, but now you're keeping indices straight. You've had to map what these indices are so that you can actually do this. Or you've stepped all the way to unsafe, which looks almost identical to the DBB code, because let's face it, DBB is basically just a wrapper on unsafe. None of this code is fun to write, none of it's fun to maintain. And you really shouldn't be here if you're playing with unsafe. No reaction to that?
Everybody gets up and leaves.
So in packed, right, I can write the code that I want to write. I can access the data off heap. I've got my target is null. My offset points to this data. It's really nice, and it manages the indices for you. Great. That's a very quick overview of packed. It's a quick look at what packed is. I don't want to spend too much time talking about that, but I do want to look at some of the design challenges we ran into with packed, some of the things that made it hard for people to pick packed up and run with it. So one of the first things is the annotations. For a number of reasons, mostly related to making it easy for the JIT to optimize things, we require that you had to say import packed for any packed class you wanted to reference. This is very painful for people to writing the code, because they then need to know every class that gets referenced in their class. They need to declare it as packed, and as they're modifying their system and making things packed, you have to go back and update all kinds of places that now need these annotations. Packed array types, or any type that you want to be packed, has to descend from packed object class. Primitive arrays aren't interoperable with packed arrays, and it's not quite conventional Java. So let's take a look at some of these in a little more detail. So for packed objects, we put packed object, the class, under the object hierarchy. Good. And so any class that you wanted to be packed had to be a direct subclass of packed object, or a subclass of an abstract class under packed object, which used up your I want to inherit from something single slot that you get in Java. It also meant that you had to fully buy into Pact. There was no way to use Pact here and use something else somewhere else. If you had some kind of structure you wanted to talk about, you were buying fully into Pact, going to retrofit your code to use Pact in all places.
Dan, clarification, if you don't import Pact, does that become an error or does it degrade to a normal heap object?
That's a really good question. The question was, does it degrade? Is it an error or does it degrade? I believe it degrades, but it depends on which version of the prototype you were running on, and it's hard to keep them all straight. Right, and so you had packed arrays for these things, which were very nice. They flattened your data and they got good locality, but they couldn't interoperate with byte arrays. You had to do something to mediate from your packed thing to a byte array. And we can't really reuse the existing Java syntax for a lot of concepts because they're different. What does it mean to put an object or something into a packed array? It's really more of a copy than an assignment. And if you make equals do the copy, it may not operate in the way people think, right? It's very easy to break users' mental models. And we saw this a lot with our research teams and our test teams who tried to take Pact and use it for different things. They were constantly struggling with, wait a minute, this doesn't quite mean what I want it to mean. Packed arrays, right? So, assuming my array is a packed array, and I'm not using the copy from syntax here, so the syntax isn't quite right. Ignore the improper syntax. The point here is that once you put your point object into that array, and then you go to take it out, you've created a new header for it, so they're never going to be equals equals. At least not in the interpreter. So this code that if statement is never going to be true. Now the caveat on that is, if things get hot enough and you jit away that extra header, this might suddenly become true. This is really not what you want. So nested fields. If I've got my packed line and I want to initialize this nested field, I can't use equals. These aren't reference fields, right? So if I create a new object, I can't use equals to assign it. That's not really what it means. I need some kind of copy or some kind of initialization for it. I need some way or some set of default values for x and y. When I've created my line class, what values do I set to x and y? It's got them in line, right? So I've pre-allocated that memory. Do I set them to 0? Do I set them to something else? Okay, it's a prototype, so maybe we just explicitly assign each of the fields ourselves. Anybody doing this is going to grumble a lot, but you can make it work, which can let you, move forward and see what other issues are still in this prototype. Until somebody declares point to be final, or start and end to be final. Now I can't do this, Java-C starts to fight with me. And yes, I can go hack Java-C for this, but what does the semantics of this actually mean, right? It becomes a user's mental model problem of how do I teach people to treat things as final? What does it mean when I put them off heap? Final may be something that we can enforce from the Java side, but there's nothing going to prevent the native side from modifying it. If the native side modifies it, what does that mean for when I have to read that data, when I can cache it, when I can skip reading it? Volatile starts to run into similar problems. We have a copy from API, and it's easy to change the values of x or y without triggering the volatility checks. Identity, right? I've got two packed lines that point to the same native data. They're not equals equals, but the data is the same. What does that mean for people? How do users make decisions about this? What kind of invariants can you build into your system when your data can be changed by some other object? This is not the semantics that Java typically has. Right, and the same problem, what does synchronization mean in this model? What kind of invariants can I impose on things when synchronization doesn't really mean anything? I've got lots of ways I can point to or reference that data and modify it. and none of them can be, if I had some invariant that said I had to modify them or limits on what the values could be, I can't enforce that using synchronize. Finalization. When am I free to finalize this particular object, right? Point 0 isn't referenced anymore. Can I finalize it when it's not referenced? Can I finalize it when polyline isn't referenced? How do I explain that to a user? Weak references are really the same problem, same with soft references. What's the lifetime of this object? And you're thinking, okay, well, whatever, you don't use that. Well, then when do I know when it's safe to free that memory? How do I know when I'm okay to tell the OS to let go of the native memory? So that's a bit of a look at some of the issues we ran into. So next, let's take a look at sort of where we've taken our packed experience and how we're pushing this forward. So we've looked at packed. We looked at some of the design challenges we've dealt with. The prototype's been good. It's helped us move forward on looking at things like flattened data, looking at off-heap access. Right? Remember, this talk is about experience. It's an experience report, and it's helping drive where we go from here. So we had a bunch of goals with packed. I've shown these earlier. A number of these fit very nicely with Valhalla, right? These are about flattened data, which I'm hoping, or I think Brian and company are talking about later. Great. There's lots of overlap here between the on-heap packed and value types. All of the off-heap stuff fits very nicely into Panama. So we look at it as we have some experience from packed objects. We have some experience from other areas. We have DDR, which takes the VM data structures and stores layout information for them and then lets us debug with that. Bjorn will be talking about that later today, I believe. And we want to take that experience and help drive it into Panama and Valhalla, and we want your experience in there as well, right? I'm repeating this over and over again because it's really a call to action. This is a room full of people who care about native data, who care about the JVM and the future of Java. And so if you're not speaking up, we need you to please get involved. So, shifting gears now a little bit, what's layouts? Layouts is where we're going. This is the next set of prototypes to address native data. So a lot of the information that I'm going to talk about here is from the state of the LDL, or layout descriptor language. We've been posting this on GitHub and pushing it to the Panama Spec Experts list fairly regularly. Please take a look at it offline, share it around, comment on it. So what's the problem that we're trying to solve? All right, let's step back again. We've got your language runtime, and you want to access that great C library, and you don't want to write JNI. You want to do something from your OS that isn't standard Java. NIO2 is great, but it doesn't cover everything. You've got some legacy system, and you want to interoperate with its data. I list COBOL here. We've got a lot of mainframe customers who are still running a lot of COBOL. Or you've got some awesome hardware. RDMA, you want to drive that I/O from Java. You've got some GPU, you want to drive that compute. How do we increase static locality and remove copies? Well, you can play JNI. Nobody likes JNI. You can play the offsets game, doing unsafe or DBB, but both of those are hard to keep up to date, especially as your systems are modified, right? If you modify the layout of your native structure, you have to come back and modify all your Java code that deals with it. You could use packed objects, but what we really need is a better way to do this. So if we keep looking at our problem, we have some kind of native data. It might be C or C++, it could be COBOL, it could be network packets, POSIX structures, protobufs, key value stores, whatever this data may be. It's something you want to interoperate with, and it's not something Java knows about. But that data doesn't live on its own. It comes encompassed with an environment. Is it 32-bit? Is it 64-bit? Did you compile with Pragma packed? What kind of padding did your compiler put in? Are you on a bigger little endian platform? Is your structure defined to be a certain endian, like a network packet? Which compiler did you use? Which OS are you on? What library versions? Right? There's lots of things that come together to tell you what your data actually is, and you need to be able to look at all of them as a big piece. So you take your native data and then you need something that you can program against. So you need some way to take that data and express those offsets, express those bits in something that you can work with. We're calling that a layout descriptor language. You also need something you can program against, so some kind of stub interface. Generating the LDL, right now we don't have a tool to do this yet, but we do have people working on tools to try and make this work. Particularly the first thing we're looking at is C and C++ headers. So with packed, I said you had to be a subclass of packed object. One of the benefits of using interfaces here instead is that you can gradually migrate your system to this. As a user, you can implement that same interface, provide the implementation that you want, and for the things that are off heap, you can use the same interface and deal with the native data. It just lets you abstract nicely over it. This is good. It may have a JIT cost the more times you implement that interface. So I've got my native data, I've got my stub interface, and then I've got some runtime behavior. So, ignore the use of unsafe on this slide. It's just there to get me my native address. But I have some layout factory. I get the factory. I ask it to map my layout, which is some point class, onto this address, and then I can just operate on it using methods. Right, so this is a very unsafe way to work. There's nothing saying that you actually have to have allocated the memory you're trying to talk to. Right now, we're allowing just passing any address through, which is not, the end goal. So one of our prototypes has a layout factory that looks a little bit like this. I know there's a lot of text on this slide. I don't actually expect anybody to read it. It just shows some of the ways we're looking at how do you map layouts onto data. It might be you have a long address like I showed on the last slide, or you might just want this to be some address or some memory allocated on the Java heap. Maybe you have a byte array. Maybe you want to create an array of these things. And so we've got different APIs for each of the one-dimensional array or two-dimensional array or whatever it may be. This is not a final API, right? This is just something to let us explore and prototype and play with to find out what the right direction is. All right, so that's sort of the native data and the runtime system. Now we need some way to describe how this is all going to interoperate and how it's going to work. So the piece that describes it is the memory model. This gives us the meaning to what those bits are, gives us the meaning to how we access them. There are many diverse languages with specific rules regarding data access. We can't describe them all. We can't give you the answers for all of them. So we're going to look at some of the most popular languages for dealing with native data, which if we look at TIOBE, Java's the #1 most popular language. That's why we're here, right? C and C++ are the next most popular. These are sort of the common language for data access. So any memory model we provide should be fairly consistent or compatible with C and C++. So we take a look at what the C and C++ memory model says. It says memory is really an array of bytes. And then it points out a couple of interesting things that I've underlined here, that memory locations are what matter. And these matter to deal with concurrent access. If two things are in the same memory location, writes to them are allowed to interfere. The reason for this is it means that the compiler can take certain liberties when it's reading and writing data. And those liberties are well understood by compiler writers, makes it easier to optimize. So that's something we want to keep. Right? To show what this actually means, if we look at two structures, the only difference between them is that one of them has this extra zero length bit field, and that has forced the two container version to have two memory locations. So if I have two threads writing on them, one of them is going to interfere in the one container model, and in the two container model, this is actually safe. I don't have interference right now. Right? This is because they're two separate memory locations. Okay. So, layouts need to have some similar memory model. They need to have some way to talk about how the bits are laid out. So we've got fields, which are a continuous sequence of bits, and we've adopted an LE-centric bit numbering scheme. And then we picked containers rather than memory location. which is very similar. It's basically the same idea. And we've allowed you to specify the containerization in your layout descriptor. So if two fields are in the same container, you can say that. If they're in separate containers, you can say that as well. I tried to find out, from my notes, why we picked the term container instead of memory utilization or memory location, and that rationale seems to be gone. So we may end up switching that. So looking at this again, right, I've got a field. It's some sequence of bits. Fields are collected into containers. It might be one field per container. That's up to you. Containers are about concurrency. And then I've got the idea of unions and arrays, right? If you've written C code, this is very familiar to you. A union is a group of overlapping members. So overlapping sequences of containers, and an array is a sequence of containers of the same type. All of these things are members. So if I want to talk about a union, really, a union is a sequence of overlapping members, which all boil down to a set of containers. Right? We're talking about how the bits are laid out in memory here. And this is sort of text that describes the same thing. It's taken from that state of the LDL document. So, tearing. Early Java allowed 32-bit machines to tear longs. There's points at which atomic writes can't be done, and we have to allow tearing. So anytime you're writing inside the same container, the model has to say you're allowed to modify these things, and writes may interfere with each other. If you're accessing separate containers, they can't. And then we want to have the idea of atomic. You may have some invariance when the data that you're writing gets written into memory that you don't want somebody to be able to read partially written data. So, to force this in, we've said maybe there's a reason to make containers atomic. Now this is sort of a best effort on the VM's part, because if you've specified an absurdly large container, there may be no way for us to actually do that atomically. We could take locks on the Java side so that the Java side is consistent for this, but we can't force the native side that you're talking to obey the same rules. And then the last piece of data access has to do with endian. Are you big endian or little endian? What we've said is that containers have an endian. You can define whether a particular container is little endian or big endian, and that tells the runtime system how to read that data. Alignment, very similar to C. The alignment is for the entire container, and it's based on, the entire layout, and it's based on the maximum required alignment for any particular container. And the way you do that is sort of a recursive. You walk through each of the members in your layout, find their containers, round the size of that up to 2 to the n to get your number of bits, and that gives you what your overall alignment for the thing is. So that's how the bits get laid out in memory. That's some of the data access patterns for it. And then you need some kind of type information to tell you, how do I access this data, or what's the meaning of this particular sequence of bits? So there's primitive types in Java. When your data maps to the primitive types, that's great. Unsigned throws a bit of a monkey wrench into this, as native data frequently uses unsigned. Java 8 helps us a little bit by adding some methods to classes like long and integer to deal with unsigned math. It's still not a perfect answer. The other thing I'm going to have is structured types. This is where I've got a layout and I want to add, this is my packed line where I have my point inside it. I need some structured layout to describe the points inside so I can talk to them. The accessors for these are going to give you back another layout instance that points to the same thing. Arrays and nested layouts are the same. Then I've got raw types. Maybe I've got some sequence of bits in here that I don't care to give a Java meaning to, or I don't have another structure to map to it. So I would give you back, maybe a byte buffer here to be able to do your read and your write. This could be for things where there's no suitable Java type to map it to, right? If I have a 128-bit integer in my native side, I don't really have anything in Java that I can use to talk to it. And then I've got pointer types. I may need to be able to walk through a linked list from my native code, and I need to be able to have the right kind of abstraction to do that. And then I've got opaque types. All of the bits in a layout need to be exactly defined, but you may not want Java to be able to access all of those bits. So there may be pieces in there that you say, this is opaque, don't give me bits for it. One area where we're not clear on what the right answer is how does this play with raw bits, right? If I asked for a raw accessor on my whole layout, do I have to disallow access to pieces that you've marked as opaque? And then effective addresses. Right, this is really the C's address of a struct field. It becomes really important for cases where you've got some kind of header, you've read the header to decide where to pass the data to, and then you just want to pass the address of that data out. You don't want to expose the address pointer operations to Java code because it's very easy to get them wrong, right? It's easy to incorrectly index something or index outside of your memory. So if you kind of wrap it inside an effective address call, you've limited where this can go wrong. We found this really useful in our DDR code, which is our dynamic dump reader stuff, for dealing with self-relative pointers. Rather than having everybody implement that, where for anybody who doesn't know, a self-relative pointer takes the address of the field, adds its value, and turns that into the actual pointer. We use that a lot for dealing with ROM data. This makes it really easy for everybody to easily do those kind of operations without having to manually do it everywhere and get it wrong. All right, so that's sort of a whirlwind tour of the layout of the bits, of the data access, and the type information. But there's a lot of open issues. There's a lot of stumbling blocks still here. This is about the experience we've had and some of the issues we see going forward. For anybody who's written a language, you've probably run into Stackmap tables, everybody's least favorite verifier-related class. Brian's shaking his head over there. These are a horrible, horrible structure. And I'm only showing one of the frame types here, but this has a fixed header and then a bunch of variable data. Now you can't process this nicely with a structure in C either, but it has this fixed piece. That I can give you a struct for. And then it's got this variable piece, and it's actually slightly worse than this because it actually has two variable pieces. So how do I deal with this in an LDL? I can't describe the full thing. I don't even know how big it is up front. How do I process this structure? I can describe the first piece of it, but then how do I safely take that locals pointer or the address of that and cast it to something else to read it? Maybe I use a raw accessor here and I read a byte, figure out what it is, and then I can cast it to the next substructure and walk my way through memory. But again, this is a lot of unsafe operations. What if the memory I'm trying to talk to is smaller than what the structure says? Or have I done the math wrong? How do I ensure the safety of the JVM that dealing with this kind of thing isn't going to crash you and crash you hard? Right? And the memory lifetime. We looked earlier at some of the issues with packed objects on finalization and weak references. How do you know when you're safe to free this memory? How do you set up the life cycle for this memory? What's the contract between the two sides on when it's free or it's safe to free them? Maybe this isn't a problem for the LDL. We just take our hands off and we hand the problem to the users. But those types of solutions always come back to hurt us in the form of customer issues. When I'm debugging the crash because somebody's done the wrong thing, I really wish I would have put a bigger seatbelt on. So, what the right answer is here, we don't know yet. If you've got experience dealing with this kind of problem, let us know. And security, right? A lot of this comes down to what's the security model here? Is it a easy to climb fence that if you want to crash your VM, we say go for it? Is it some kind of razor wire wall that we don't let you cross? Java has a culture of not crashing. If your VM seg faults, that's a serious problem. We get lots of very unhappy customers when that happens. There's security implications of this. So we really need to make sure that whatever model we expose from LDLs tries to help you do the right thing. Native culture is, if you do the wrong thing, congratulations, blow your foot off. That's really your problem. But that doesn't really work with Java. So how do we marry these two very separate and very dilute cultures together? And then, there's all these existential questions. Who am I? What's the meaning of life? No, wait, sorry. What's my identity? right? A lot of them come to how do you say this is that piece of native data versus some other piece without giving people direct pointer access. There are answers here, there are things we can try. We don't have all the answers, right? Again, this is about experience. Sorry to pick on you, Brian, but your quote here is good. You know, the prototype LDL grammar that we had picked was horrible. It was hard to parse mechanically and hard to read for humans. It's one of those things that grew organically. It was a little piece here and a little piece there, but it ended up just being bad. So we've kind of flushed that and moved to stepping back, looking at the model. And how do we get the model right so that, you know, when the grammar comes out later, it doesn't matter as much. So again, you know, I'm here to tell you to get involved. If you care about native data interop, get involved now. Join the Panama Spec Experts list. Get involved with Project Panama. Surface your use cases. If you're dealing with, you know, unsafe memory, native memory, if you're dealing with J and I a lot, we want to know what use cases are you using? What things do you care about? You know, take a look at the state of the LDL document. Comment on it. Let us know areas where it seems to have missed the boat. We don't have all the answers. What we're happy to do, though, is work with you to find what the right answers are. You know, try out prototypes as they become available. You know, poke at PACT a little bit. See what pieces that work well and what don't for your use cases. And one of the other things we need to know is, have we gone too far? Are we trying to solve too many big problems here? Should we step back further and give something simpler and smaller, right? Our use cases are, we have those and we know our internal teams, but we don't know what everybody else is doing. So please, you know, get involved. And this, of course, is my legal notice slide, because no conference is complete without multiple legal slides. Any questions? Yep.
Well, it's not a question, but when it comes to data layout language, have you looked at there's an old but quite powerful standard called ASM.1? Are you familiar with it?
No, I'm not.
It describes the layout of data over basically for serialization. But it's quite powerful, and it can handle those variable-sized structures like the Stackmap.
I agree. It also has like the parser libraries written already. So
Yeah,
Woohoo.
it has parsers and generators for pretty much every language in existence. I don't know, it's probably 20 years old, but it's constantly maintained, and it's an industry-wide standard for data layout.
So that was ASN.1? Okay.
Specification or syntax notation. It came out of the PKCS standards, CCITT stuff like 20 years ago.
And that's why we come to these conferences, right?
it's used for X509 certs.
Okay. Thank you. I will take a look at that. Jeremy?
So it seems to me that and I haven't looked at your spec at all, but it seems to me that you don't want people writing these things. That you want it to be emitted by tools that understand the source language and consumed by tools that understand, that consumed by the JVM directly,
Yes.
something like that, and perhaps you would run it through a tool that emits fluent Java. And that would overcome issues like the ones you brought up where, oh, well, we can't guarantee atomic in both C++ and in Java because we use not. Well, if you automatically generated all the code, it could be, you could have the atomic keyword in C++ and you could translate it to something that understands that in Java. So why is readability for anybody other than the hardcore, extremely dedicated people who want readability an issue? And that's not really the question I'm asking, but could you comment on what I just said?
Okay. So the readability matters because there are languages that aren't easy to parse, right? There's no standard definition of network packets. So I need something that I as a human can go.
There's always an IDL. Right? I mean, there's always like, okay, I wrote some higher level thing and something turned it into something that looks like a network packet.
Yeah.
Maybe there's not.
I'm not aware of anything for network packets. And we took a quick look. Everybody likes to draw pretty ASCII diagrams or write, you know, a description of it, but there's not a well-defined, here's something you can grovel.
Well, I could imagine something relatively straightforward for a network packet just because it's, this number of bits and not like C++ where you have to encapsulate the notion of atomic.
Yeah, I'm not arguing that readability is the main goal. Today we're actually handwriting a lot of these, but we do have people working on tools. We're internally calling them grovelers to go read your C++ header files and generate the Java side for you.
And the other thing was I wanted to ask is the repeated field thing doesn't really seem like that difficult an issue to solve. I mean, there's always a field that tells you how many of something there is, and then and then a repeated field which can count up to that number of times. Is there some way to solve that relatively? I mean, I don't know.
You can.
I don't understand why that's hard.
It's not the. Sorry, the question was why is the variable size data structures hard? And the answer isn't that it's technically hard, it's that it's hard to do that in a way that doesn't make it easy to crash your VM. Right?
Well, it's all automatically generated from some description of the descriptor language. You don't have to worry about it quite as much, right? Or are you
I could make that same claim about Java code, but as a VM developer, I still care about the specification at the bytecode level. Just because Java is automatically generated into bytecodes doesn't mean that nobody else comes along and writes horrible bytecodes that go overwrite, the zeroth argument in my.
You don't mean that the user is likely to do something that's going to crash the VM. You mean it's just hard to get the implementation right.
The implementation has to be correct. You need some way to handle that kind of data, and there are times where it's going to be wrong, right? Customers get things wrong all the time.
Yeah, I mean, okay, okay.
Right, it's enforcing that JVM safety in there. If you've got smart users and they're willing to do a little bit of debugging on their own, you can usually get the right thing, no problems.
What about more complex variable length structures like something that, like the copy things like varants followed by the number of fields, where the length of the description of the field isn't fixed like 4 bytes. It's something variable length in of itself and requires a more complex algorithm to decode.
Yeah, it's a lot of the same problems. I mean, we have UTF-8 strings, or Pascal strings, right? They have a length and then a certain number of bytes. All of these come down to the same problem of how do you do that safely. It's not that it's impossible to write the code to do it, it's how do you get it right.
What I was getting at is in the descriptor language, the description of how you decode the data might actually require a small program.
Yes, and that.
We want variable size. Go and look up all the different kinds of variants. You don't need that. I know you already have.
Yeah,
And there's no way that's all going to get into the layout language.
totally, which is, I think, the exact
Which
problem.
is another reason we want to do SN1 because it has its own variant. There's this, like most packet languages commit to some kind of variable length something or other, like a counted array, a variant, or something. That's not what we're trying to design here. If I understand it correctly. We're trying to understand the next lower layer that lets you pull up the bits, and then you can write simple, safe Java code that will parse the variable, the parts that are more complex than just the simple bits.
And that's why I sort of go back to what I was saying before. This really feels like something where if you have something like this, somebody needs to, for any target domain, you need to build a set of tools and compiler output and libraries to deal with variant encoding and decoding around it. And so for individuals to try to do this, sort of like that, wise madness, I guess. So it's presumably there's, and I haven't looked at it, I probably should have, because I'm very interested, I have relative use cases, but presumably there's a way to plug in things like a variant encoder or a decoder in a relatively straightforward way.
We're trying to hike the safe side of the mountains of madness.
Thanks, everyone.